Welcome, fellow chemists, to Unit 3. We're going to study atoms, a little bit of history, and also their structure. So first, for their history, our first person that comes up is Democritus. Of course, some stuff happened before, but one noteworthy contribution of Democritus, and this is a couple thousand years ago, he came up with the term atomos, which is Greek for no cut. So that's where we get the term atom from. And then shortly thereafter, Aristotle, he came up with the idea of four elements. Be a much simpler periodic table if it weren't for some other people after him, but that's what Aristotle came up with. Now, after that, you might notice the date says 1766. So in between those two, most of what was done in chemistry was considered magic and alchemy and trying to find all sorts of magical ways to turn lead into gold and the search for the fountain of youth. So Dalton's ideas were awfully controversial since we'd been practicing alchemy for many hundreds of years. He came up with four ideas. He said that everything's made of particles called atoms, so he borrowed one of the terms from earlier, and he said that all the atoms are identical. So he kind of hinted at there's probably a lot more than four elements. And the third thing he said is that you can kind of make compounds by combining the atoms. And the last one was the most controversial. He said that atoms aren't created or destroyed, they're just changed. So he kind of mentioned the law of conservation of mass / energy. So that was a very controversial idea because at the time people thought that you could make something from nothing and have things disappear and reappear. That was part of the magic behind alchemy. So his Dalton's theory was accepted by some, but not by all. Now, after that, many scientists started making some serious progress. We had J.J. Thomson. He kind of made the cathode ray tube and did all sorts of experiments to find the electrons. So he had something like that. And an actual picture of his device is shown there. One of the more noteworthy scientists is Ernest Rutherford. And here's a picture of what he did right here. He wanted to find out if an atom is full of stuff or if it was mostly empty space. So he shot some uranium particles through gold foil, and he found out that not much bounced off. So this was his model of the atom. He found that the very middle of the atom is positive, and the rest of the atom is mostly empty space. So that's kind of what our current model shows. Now Bohr, shortly thereafter, he came up with this model. It's not correct, but it's really, really helpful in knowing a lot of how the periodic table is arranged. He said that the protons and neutrons are in the middle, which is correct, and he said that makes up the nucleus, which is really small, and that's also correct. And he said the electrons are on the outside, which we all agree with, but he said that the electrons orbit much like planets would around the sun. So he was very close. It was just that last detail, and our current model is kind of more disappointing. It would look like this, where there is a cloud of electrons somewhere, and then we have the nucleus on the inside. So an analogy for how much space this nucleus takes up and how much the electron cloud is, we have this right here. First of all, nucleus has a small volume but big mass, so nucleus is super dense. And here's the analogy. If the atom was the size of the dome, the nucleus would be the size of a marble in the center of the dome. So the nucleus is incredibly dense. You can, of course, pick up a handful of atoms. You can pick up a block of gold, a block of ice. You can pick up a handful of something. But the nucleus is so dense that you could not physically pick up a handful of just the nuclei. Okay. Now, we're going to use several different symbols for particles. We're going to see E minus for electron, P plus for proton, and N0 for neutron. So it's a little bit of time saver just to write those symbols rather than the entire word. And let's see, sometimes we have representations like this, where you'll see the atomic number at the bottom and the mass number at the top, whereas other times you'll see it an entirely different way. You'll see the mass number at the bottom and the atomic number at the top, but they all show them in all sorts of different places. But the big difference, the one similarity between all of them is there is a big number and there is a small number. So I'm just going to kind of look at this one. This big number is the mass. That's how much the protons plus the neutrons is. And this right here is just the protons. Okay. Now every periodic table is going to have, for carbon, the 6 and the 12. So it doesn't matter if it's at the top left, bottom right, the middle, anywhere. We're just going to think of it in terms of the small number and the big number. So the small number is always the number of protons, and you can't change it. The big number is, on average, the mass of that atom, adding the protons plus the neutrons. So I'll draw a little thing here. This is our protons, and this is our protons and our neutrons added together. Okay. Now, let's go a little bit farther down here. There are a few different ways of naming these. Sometimes we will say that carbon -12. So instead of the previous one where we had the C and the 12 beneath it, sometimes we would just write C-12. And sometimes we'll even make it shorter, where we would write just the symbol that we would see on the periodic table. So instead of writing nitrogen dash, we can just write N dash. And if you take a moment to look at this 15 and then look at the periodic table, you'll notice that nitrogen has a 14 for its large number rather than a 15. Well, remember, on the periodic table, that large number is the average. So N15 can exist. So can N16, N13, and N12. But on average, that's what the periodic table shows, is the average mass for that element. Okay. Now, one important thing to also remember is, let's go back to this carbon example. The 6 can't change. Okay. We can have carbon 14, we can have carbon 13, we can have, well, carbon 12, like it shows in the periodic table, but you cannot change the 6. If the 6 changes, it is no longer carbon. If we change it to 7, well, take a look at your periodic table again. You'll notice that nitrogen has a 7. So that number of protons is what distinguishes one element from another. So I'm going to pause right there. Now we're going to continue and do a few practice problems. Which element has atomic number 47? If you look on your periodic table, you're looking for the small number that has a 47, and you should find Ag, which is silver. And if you're wondering how many protons, well, it has 47. You can't change 47 or else it's not silver anymore. And let's see. Another question you might ask is, all right, for silver, how many electrons does it have? Well, since we don't show a plus or a minus for silver, it's going to have the same number. It's going to have 47 electrons. So the nice thing about it on the periodic table is, if you see the small number for that element, it tells you how many protons and how many electrons for that element. So if you get a tougher one, if you have a -1 or a +2, that tells you that there's a different number of electrons. So fluorine, let's take fluorine for an example. Fluorine has, its small number is 9. So we know that it has 9 protons. Now, in order for it to have a -1 charge, it can't have its normal 9 electrons. So it's going to have 10 electrons. Calcium is another good example. Finding calcium on the periodic table, it has 20 protons. Now, in order for it to have a +2, it needs to have 2 more pluses than minuses. Calcium would normally have 20 electrons to balance out, but in this case it's going to have 18 electrons. So 20 minus 18, it has 2 extra pluses, 2 extra protons. And now we're going to look more closely at the mass number. The mass number is the number of protons and neutrons in the nucleus. So this other term is an isotope. An isotope is when you have different numbers of neutrons. So here's an example on the screen. There's carbon 12 and there's carbon 14, but they're both isotopes. Carbon has always 6 protons. If it didn't have 6 protons, it wouldn't be carbon. And in this case, I don't see a carbon +1 or a carbon -1 or anything like that, so we know that it probably has 6 electrons. Protons and electrons are usually even unless you see a charge on it. And take the neutrons, well, we know it weighs 12, so 12 minus the 6 protons would tell us that it also has 6 neutrons. Okay. Now, carbon 14 is heavier. Carbon 14 still has 6 protons, or else it wouldn't be carbon. It doesn't say that it has a positive or negative charge, so we're going to assume it's neutral. It still has 6 electrons, and this time if we subtract 14 minus the 6 protons, this one has 8 neutrons. And so that's how we can have a heavier than usual isotope of carbon. So again, looking at the periodic table, carbon on average usually weighs 12, but you can have heavier versions of carbon. So here's a few more examples. If we take the mass number minus the atomic number, we get the number of neutrons. So here's one right here. Chlorine 37. We want to find out how many neutrons. Well, chlorine has a mass number. You'd have to look on the periodic table. Normally it has a mass number of 35. But this time it's a heavier than usual one, and that's fine. So we would take 37 and we would subtract its 17 protons. So we write the 17 protons there. We would have 20 neutrons. Okay. How did we know it had 17 protons? Well, it is chlorine. It doesn't have anything other than 17 protons. And if we were curious about the number of electrons, well, it would have 17 electrons as well, because the protons and electrons are always the same unless we see something like this. A Cl with a -1 or a Cl with a +1. So that 37 is not its charge. The 37 is the mass of that particular version or isotope of chlorine. So this is great fun. Let's do another one. We have here bromine. Took a second there. How many protons, neutrons, electrons in bromine? 80. Well, looking at bromine on the periodic table, you have to look on the very far right. It has a mass of 80, 79.9 on the periodic table. That rounds to 80. So what you see there on the screen is its normal isotope, and its small number is 35. So we know that bromine has 35 protons. And since it doesn't say anything about a charge, we know that it's also going to have 35 electrons. Okay? Now to find the neutrons, we're going to do 80 minus 35, and we will get 45 neutrons. So that's what bromine typically has for protons, neutrons, and electrons.